Is it fine, sir? Hello? Hello? इसको बोलो.
Yeah, so I'll be presenting these two papers. One is direct preference optimization, DPO, and another one is group robust preference optimization, GRPO. And he will present the third paper, which is SIMPO, and then we'll be giving our project proposal. So before we present the DPO, so let's first recap what is RLHF. So we generally use RLHF in the LLM fine tuning so that it can generate the outputs which are more closely aligned to the human responses. So we collect the data in terms of human feedback. So we give two sentences, let's say this winning sentence YW and then the losing sentence YL corresponding to the prompt X, and then we collect this preference data set. So the first stage of RLHF is supervised fine tuning. So we take a pre-trained LLM by pre, and then we apply the pre-training objective. Basically, we do instruction fine tuning on the given task, and we obtain a reference policy model, which is PyRef. And we need this reference policy so that when we apply DPO or RLHF, the output is more closely aligned towards the PyRef. So it does not deviate too much from our reference policy. And the stage 2 will be reward modeling. So since we are collecting the preference data set, we need a model to know the reward of a sentence pair, let's say X and YW or X or YL. So for that, we have a model called the Bradley-Terry model, where we generally model the reward model. So the reward model is parameterized by phi, and the probability of YW is preferred over YL given X is given by the softmax representation. And generally this, we want to minimize the negative log likelihood of preferring the preferred response YW over the dispreferred response YL. And this is the standard negative log likelihood. Next. And the stage 3 will be standard RL fine tuning. So after the reward model is learned over the preference dataset, then we want to use reinforcement learning to steer the model. We can use a very popular algorithm, for example, PPO, proximal policy optimization, or we could use any other algorithm. So this is the objective of the reinforcement learning. So we have the reward, which reward is coming from the reward model. And then we also add a regularizer term, which is the KL divergence between the policy and then the reference policy. So this term is added because if we don't add this term and simply try to maximize this objective, then the output will be very unnatural because it will be too much deviating from the reference policy. So there are some challenges in the RLHF part. So the first challenge,
there are places where the reference policy is playing a role, right? So
sorry,
the reference policy is playing a role here.
Yes.
In the RL part, but even in the Bradley-Terry model, we go back to the previous slide.
Yeah. Yes.
Yeah, there's a role that the preference models play here also, right?
You mean in equation 2?
Yeah.
I mean, here it's simply the right. I mean,
Equation 3.
Equation 3. Yeah, I mean, this is the likelihood of this equation 2, right?
There's no preference other than the data set here. You're saying this is only the preference data set, right?
And yeah, I mean, we can think about R5 as simply a neural network, and we are passing the sentence pair X, Y, W, and it is giving just a single one. There is no reference model.
Okay, so there's no PyRef is not part of
no. In the Bradley-Terry, no PyRef. Yeah, previous one. Yeah. So the main challenge with the RLHF is that the complexity, because as you have seen, we need 3 model in the memory. We need the reference policy, we need the our original policy which we are trying to fine tune, and then we also need the reward model. So that is computationally expensive. And then this RL fine tuning part is generally costly because it needs the sampling. The PPO is an online algorithm and we have to sample the response from the model. So it is a very costly procedure. So this from here, from the disadvantage of RLHF, we can motivate the use of DPO. So the DPO generally avoids the stage 3 of the RL fine tuning. So in the RL fine tuning, we can generally avoid this RL fine tuning part and we can explicitly model the reward, which is R5. So this is why we ask the question, can we eliminate the need of the complex and costly RL optimization? And the answer is DPO. So yeah, if we start with the RL objective, so in equation 5, it is the standard RL objective. And then for a fixed input X, we can now write this as in terms of a constraint optimization problem. So this is the optimization objective. So we have just expanded this expectation. And this is the KL divergence. And the constraint is that the policy should be a valid probability distribution. Yeah, next. Now we are going to solve this constraint optimization problem. And
but isn't the limitation here that you're still, where is the human feedback? It is only in the, it is all respondent. It's all retrospective, right? People give preference X, Y over YL. But where is the, there is a human feedback is not part of it, right?
The human feedback is there, right? In the expectation, we have the X and the Y. So actually, we have solved the optimization problem, and the solution of this problem will actually incorporate. So currently, in this optimization problem, we have pi, over which we are trying to maximize, and we have R. So if we don't try to model this R, then we want an expression of R in terms of pi. So we want to connect the policy and then the reward model, such that we can get rid of the of this reward. So that is the main objective. Yeah, next. So the so we can construct the Lagrangian here. So the Lagrangian is like we introduce the Lagrange multiplier, and the Lagrange multiplier is only the function of x. Then we take the derivative of the loss function with respect to pi, and then set it to 0. And after doing some math, we can see in equation 12 we get an equation which has the policy and then the reward, and then we have an additional lambda prime, which also we can get rid of. Yeah, next. So yeah, if we take the exponentiation of the previous equation, we'll land into the equation 13, and there this term exponent of minus lambda prime x can act as a proportional constant. So we can get rid of this term by introducing the proportional constant, so that the partition function will become simply the sum over all of this, because it is a valid policy. So here in equation 16, we can see that we have obtained an optimal policy pi star, and that is dependent on the reward Rxy. And now we can parameterize our policy and then the reward. So now this partition function will also be dependent on the parameter phi.
Why are we fine doing an exponentiation? Why won't the equality change?
Sorry?
Why is exponentiating not changing the equality?
Go back.
After all, you're trying to solve an optimization problem.
Yeah.
So what property of optimization are you choosing? Are you using?
Your question.
If you are, is the maximum value of f the same as the maximum value of g of f of x, given g is a monotone increasing function?
Yes, yes.
Is it?
Yes.
Is that property being used here? Is what is exponentiation a monotone increasing function?
No. We are not using that. So here, after setting it to 0, derivative setting it to 0, we have a log term sitting there. So we want to get rid of this log term. That is the reason we are exponentiating. I mean, there is nothing else. Just to get rid of log and so that we can get pi. Huh? 12 and yeah. So 12 and 13 are essentially we have just taken the
Fine. In
exponentiation
this
of
case,
this
it
previous
was just to
equation.
solve. But my question in general was, or even here they've used it, right? So, moment you take a monotone increasing function of of an existing function, optimizing or maximizing the monotone increasing function is equivalent to optimizing the original function.
Yes, yeah,
But if you,
yeah, yes.
including is used even here.
Uh-huh.
Go ahead.
Okay, so now we can see that, yeah, this is our optimal policy pi star, and that is written in terms of the reward R. Yeah, now next. Yeah, but now we have a problem with, so the problem is the partition function. So even if we explicitly model R5 based on the preference data, still we won't be able to compute the the optimal policy pi theta, because of this partition function Z5, because the Z5 is actually Z5 consists of the summation over all the responses y given x. So for a particular x, it is impossible to get all y. So that is the reason it is intractable to solve. And now we need to eliminate this partition function. So we'll do some simple mathematical trick to eliminate this partition function. Yeah, but those are also computationally expensive, right? I mean, yeah, there are many sampling techniques that we can use to estimate this Z5. Yeah, but the simple will be just to get rid of it altogether. Yeah, so we have this partition function. So it is just simply rearrangement of the policy and then the reward function. Yeah, next. The main technique that we'll use to eliminate this partition function is using the Bradley-Terry model. So the Bradley-Terry model is saying the probability of preferring YW over YL is given by the sigmoid function of the reward difference. And then if we substitute this reward in the sigmoid, then this Z5, this term will vanish. So then we'll get this pi theta, p theta of YW preferred YL, preferred over YL given X is this term. But this H pi theta now does not have this Z5. So, sorry?
How the reparametrization getting rid of?
Yeah, so if you substitute this R5 here in this equation 20, then this beta log Z5 X will be
Substitute for what? Alpha.
Sorry?
Substitute for what?
Substitute R5 X comma YW in equation 20 and substitute R5 X comma YL also in equation 20. Then this beta log Z5X does not depend on YW or YL. So this term will cancel each other. So we are getting a nice, so without ZW, we can see that we have this H pi theta, which does not have the partition function. Yeah, next. So then
Reparametrization is in terms of a log. This is log linear.
simply algorithm. Yeah, now the DPO loss function will be simply the expected value of the log probability of preferring preferred response YW over the dispreferred response YL. And if you substitute the p theta value from the above from the previous equation, then we'll get the simple DPO objective. And now the good thing about this is that we don't have R5 and also we don't have Z5. So we don't need any explicit reward modeling. We can simply train this equation, train this above equation using the preference data set, and that will give you the optimal policy. So, and then one thing is that there is something called DPO implicit reward. So the implicit reward is not same as the explicit reward. So the explicit reward has the Z5 term, but the implicit reward does not have the Z5 term. So this is simply the beta and log probability of, so the log probability difference basically, log pi theta minus log pi ref. Yeah, next. But in order to understand what does a DPO update do, it is very important that we look at the gradient of the DPO loss. Then it will give some information that what a simple sample DPO update will do. So we start with the LDPO. This is standard equation 28, and then we take the gradient of LDPO with respect to theta, and then we define internal parameter u, and then substitute it over here. And after some algebraic manipulation, we will see that so this is the equation 36. After some algebraic manipulation, I'm not going through all this. We'll get the gradient of the LDPO in terms of this equation. So this is very important because the first term says that it is the gradient of the log probability of preferring YW. So actually it is generating YW from the policy. And this one is the likelihood of generating YL from the policy. So if we want to maximize and this term is also weighted by the sigmoid function. So the sigmoid of the reward difference. So generally, intuitively, this DPO, what it is doing is that it is maximizing the log likelihood of the preferred response, minimizing the log likelihood of the dispreferred response, and weighted by the that term which contains the sigmoid, and also scaled by beta. So if this reward estimate is wrong, then it will try to make stronger out there. That is what this term is saying. So yeah, these are the 3 points.
But
ultimately,
ultimately, you're solving a non-convex optimization problem, right? This is a non-convex optimization problem, clearly. So won't it happen that if you try and increase the likelihood of preferred responses, decrease likelihood of just do both of them simultaneously, won't it lead to some local minimum? I mean, isn't this basically a recipe for faster descent into a local minimum and no recourse, no way of getting out of local minimum? Instead, if you were to be a little benign with this non-preferred responses, right? Let's say increase likelihood of preferred responses, but heuristically don't dampen the non-preferred responses. So there's a chance of escaping minimum. Sorry. It's not even concave.
Which one? 27, yeah. So if the R theta is a neural network,
Yeah.
then
That is not. So isn't it a recipe for getting stuck in some local minimum or local max?
I didn't quite get the question.
In the next slide, did you say you are increasing likelihood of preferred responses?
Yeah.
Should you not be a little careful or benign with the non-preferred responses? Why do both at the same time? Why do both? Why not do one at a time?
So we can forget about these two, and if I simply say I'm increasing the of the reward margin. So the reward margin is like the difference in these two. So this first term is the so if we take the pi ref also here. So if you go back to the previous one, just hold on here. Yeah. So this term, if we say entire term, so this is the reward margin, reward margin, not the margin, reward difference. So my objective is to maximize this reward margin. So how it will maximize? It can maximize either maximizing the log probability of the preferred response and minimizing this term. Right?
That's what exactly. Why do both simultaneously? Why not do one at a time? Why not alternate between the two? Otherwise, you'll make an ascent on some local maximum very quickly and not be able to escape it.
You mean to say like the alternate, like
yeah,
there is no explicit min-max term here. So
that's okay. This is more from algorithm perspective. We are not saying change the objective. Objective is what it is. There's no min-max like this.
So it's basically standard gradient descent they're applying.
In gradient descent, you can be very careful, right? Instead of, I mean, why is exact line search not preferred, because exact line search can get you into local maximum. On the other hand, you want some sufficient degrees condition.
Okay, okay. Yeah, yeah.
I'm asking a similar spirit here.
Okay. Yeah, actually, main paper is not talking about that. They're basically taking, yeah.
Consideration you have in mind? Think about it, reflect on it.
Yeah, so this is done. Yeah, these are the some key results. So they're showing that DPO is better than PP. That's the main takeaway from this slide. PPO, RLHF. Yeah. Next. Yeah, these are the some critical analysis. So I'll talk about mainly the limitations. So there are 2 or 3 limitations. So the first limitation is that it needs 2 model in the memory. It needs the original model phi theta, and then it also needs the reference model. So if we talk about, let's say, an LLM Llama 3, 8 billion parameter. So that model itself will take 30 GB or 40 GB of memory, and we need the twice of that. Moreover, it also needs the 2 times forward pass. So that is also costly. So these disadvantages will be covered. I mean, when he will present this Synthio paper, then we will see that some of these disadvantages will go away. Yeah, next. So this is the second one, which is group robust preference optimization, which is based on DPO, but it is solving a different problem. So the main problem is that the human preferences are diverse, meaning if we ask the same question to different person, we'll get different answer. But DPO is designed in such a way that the majority group will always win over the minority. So that is not what we want. We want to introduce some fairness over all the groups. And because of that, we have the GRPO. So GRPO is doing simply the robust minimization, robust optimization part. So if we take different groups, let's say each group is DG, and we compute the loss over all the groups, and the maximum loss is what we want to minimize. That's the standard min-max problem. And so in that way, we can introduce some fairness to our problem. Next. So yeah, we can collect the data set. For example, we can divide the data set into many groups. So for example, this X will become now XG. So this XG is actually this one, X, and then concatenated with the group information. So we have some prompt X, and if we have the group information, then we can simply concatenate it, and this will become my X. And corresponding to XG, we'll have the preferred response YW and the dispreferred response YL. And we collect all the data set, and that will become my next. So yeah, now if we derive the GRPO objective, so the first one is the standard we want to minimize phi theta, and this loss function for GRPO. So the loss function for GRPO is simply the maximization over all the groups, and we want to take the DPO loss. And the DPO loss is defined by equation 42. This we have already seen, but the only difference is that we want to compute the DPO of all the groups, not the original data set. And yeah, this is the H by theta. So, but if we simply do this, there will be a problem. So there are 2 problems mainly. One is that it is not smooth because the max operator is not smooth, and a small change in pi can cause a discrete switch in the groups that attains the maximum loss. And second, the neglect of other groups. For example, a group can give the highest loss, but there could be another group which is very similar to the highest loss, and that could be ignored. This is what we don't want it. So to solve this, we have next. Yeah, then we have this minimax formulation for the GRPO. So instead of simply taking the maximum, we introduce an adversary which is alpha. And these alphas are the probability simplex, so that the sum is equal to 1 and all the alphas are greater than 0. And instead of taking simply the maximum loss, we take the convex combination of the DPO loss. And now we have the 2 game player. One is the pi theta, another one is the alpha. And this is standard minimax 2-player zero-sum game. And our objective is the convex combination of this DPO loss. Next. So yeah, since it was a min-max formulation, now we need to so that there exists some equilibrium for this min-max problem. So this equilibrium will exist for a special case, which is if we use the log linear policy class, and if we use the uniform reference policy, then this Nash equilibrium will exist. So if we take the LLM and we pass, this xg and then y, we get the hidden representation, which is phi. And then if we add a linear classifier whose weight is theta, then this gives me the scalar value, which is f theta. And then simply we take the exponent, and then so this is standard softmax, so that we get the pi theta of y given xg. And if we take the uniform reference policy, that means that the pi ref of yw given xg is equal to pi ref of yl given xg. And now from that hw, this two term will vanish. And in the DPO loss, we will not see any pi ref, rather we will only see phi. And after doing some algebraic manipulation, this will be the final equation 49. And this is important because this equation is concave with respect to alpha, and it is convex with respect to theta. Now we can invoke the standard minimax theorem for convex concave function, which says that Nash equilibrium is guaranteed to exist. Next. And now how do I solve GRPO problem? So there is standard method mirror descent, where we so this algorithm, so this starts with sampling a group from the categorical distribution, and we also sample a data point. And finally, we get this line 6, which is giving you the weight output for the alpha, which is simply the exponent of the scale loss. And then this line number 7 also needs renormalization because the alphas are the probability simplex. And line number 8 is standard, the gradient, standard gradient. So then we can simply.
So line number 7 is simply projection.
Line number 7 is the normalization.
It's also kind of projection, right? It's projecting into the simplex.
Yeah. So here in this equation, I can also use the projection.
Yeah.
There also can be done.
So there also. But the other more important question I have is, what if we didn't want to do min-max? What if we wanted to personalize? So I have groups and I want to personalize the entire, instead of making it robust across groups, I want to personalize it. How do you think objective?
So that is our project proposal actually. So we have this privilege and the non-privilege concept that can be user specific. So welcome.
Okay, great.
So this is actually GRPO result, which shows that GRPO is better than DP, which is obvious. Yeah, and here the critical analysis is that the first limitation is that the assumption of the known groups. What if I don't have the group information? Then it could be a problem to create the data set. And then scalability is a concern, which reviewers are saying that these models are all tested for the small language model. But does this result hold in the large language model? Above, let's say 12 billion or 13 billion parameter model, that is not explored yet. Yeah, next. So yeah, from now on, he will present.
Yeah. Hello. Am I audible? Oh, okay. So in the DPO setting, we had this disadvantage that it requires loading two models, PyRef and whatever we are optimizing. So that increases memory footprint. And another problem with DPO is that the objective is like training objective is trying to maximize this reward. Okay, sorry, I'm lost. So training objective is trying to maximize this low probability, but that is being like for that we are using PyRef to maximize this. But when we are doing inference, we are not using PyRef. So that is kind of doing misalignment, which will which kind of leads to like this uh, uh, like sorry, this RDPO does not basically imply that log probability will be maximized during the inference. Yeah. Yes. Without this. Yeah. So basically, this misalignment problem, or this author of SIMPIO, they are saying that this occurs in around 50% of the time. Like they have seen this empirically. That is what they are saying. Yeah. So the motivation is that we need a simpler model, reference model, where like we don't want to include the reference model. Then one other thing is that we need the reward function that is directly related to generation process
So
where
I'm a little confused. I thought your motivation was that reference model itself is not being used
yes,
during inference, but now you are saying throw away the reference model altogether even during training. I mean,
yeah. So that is the misalignment, right?
presence of reference model was not the problem, right? The problem was it was not being used during inference.
Yeah.
They're throwing away the baby with the bathtub.
So like they are proposing like that we can just not use the reference model during training. That will also work. That is what they are proposing. But yeah, we might need to think something where at the inference time we are using the reference.
Go ahead.
So that is the thing. Yeah. So can I go next? Yeah. So the implicit reward they are defining like this, that we will just use a log probability where we will just sum over all the log probabilities. And because since if we just don't normalize it with length, it is just these log probabilities will keep on increasing with the response length. So that is a very bad thing. So that's why they are proposing normalizing with length. So the mod wise length of the response. Then other than that, they are also proposing a reward margin. So what they are saying is that instead of simply just taking difference of reward for YW and YL, we can include a reward margin gamma that will simply increase the probability of YW even more. So it is basically amplifying the probability. And yeah, so this objective function, yeah, this is the same. Yeah, so we are combining both those things, and we'll get this final loss of the sympio where we are
How did they remove the reference model? How did they remove the reference model? Based on, okay, which is the first slide? This one. But there's a target reward margin gamma.
yeah.
So instead of a reference model, that the margin is between win and loss. And there's a margin there put up. There's no
Reference model. There's no
length normalization and
yeah,
reward margin.
yes.
I mean, how's length normalization surrogate for the reference model? The reference model
No,
was,
that does not surrogate for us. There's length normalization is just for not to.
see, the whole idea of reference model was that we should be able to back off to that. Now they are just saying adding margin and length normalization. They're changing the model, but how is it compensating for reference model?
So they are saying that we'll uh, like to not diverge from the reference model. We'll set this value very like is increments and learning rate are very small. That is what they are argumenting in the paper. But since this learning rate is very small, it will like by the nature of this training, it will not diverge too much from the reference model. That is what they are saying, and they have shown extensive experimentation to show this.
Basically, this margin is an independent concept. I mean, in DPO also we have used gamma.
Yeah.
The only contribution to here is that this art in DPO, original DPO, we had this pi rest, but here we don't have any pi rest. Instead, instead of writing in reward as the ratio of the log likelihood, they're simply saying, why don't we take the log probability of the response itself and then normalize it by it so that there is no difference. So these two are two different things. We could have used gamma in DQ also.
Yeah. 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 So in the experiments, they are showing that like SimPio is actually better, and they are showing it like in the ablation stage. They are showing that if we don't use length normalization, the performance is degrading compared to DPO, even DPO. And if we use gamma as 0, then there is not much significant improvement. So this is what they are saying. Yeah. Yeah, so the critical, so major critic is that since they are not using a reference model, then that might lead to diverge. If we are doing extensive training, then the model will diverge. So that is the major critic of this paper. But I've seen the reviews of this paper, and they have answered all the critic with showing extensive experiments that they have used this for different types of, like in the chat setting, and different types of tasks as well. So they are showing that in all kind of tasks, it is not diverging too much.
We are on time.
But yeah, I mean,
5 minutes. So yeah, as you have asked, why don't we personalize it? So yeah, for that we can have the concept of privilege and then the non-privileged group. So the core idea for this fair PO is that we have a possible set of levels, 1 to T, and then we have the data set Xi and then Y. So we are basically applying it for the multi-level classification setting for the time. Later we'll also do it for multi-level generation setting. And so we can have, so this is the standard classification level. This is yi1 till yit. And if yil is +1, that means the level is present in xi, otherwise yil is 0. So this fair PO framework will help to mitigate the bias and promote the fairness in the multi-level classification. And we'll do that by applying the concepts of the GRP. So the main idea is that we'll partition the level set into two groups. One is the privileged group, another one is the non-privileged. And then using the concept of GRPO, we'll be able to do that. So the first thing that we'll do is that in the multi-level classification setting, there is a concept of confusion. So we are basically quantifying that confusion using this equation 54, where we have the confusion set for a particular level L. So this is the set of all those levels for which the level of the Y is 0, and the model corresponding to the level K is giving the higher score over the model corresponding to level L. So if L is my target level, and I take all those levels for which it is not present in the data set, but still the model is shows the presence of that level. So that is how the levels are getting confused in the set. So there are two main goals that we want to achieve. First is the privilege. So for any true positive level L, the model should be able to strongly distinguish from its confusing negative. That is our first objective. So we want this M xi WL to be significantly higher than M xi WK. And in the non-privileged part, which is not that important corresponding to that particular user, then we can use something, I mean, we don't want to, we want to be agnostic in that space. So that means that the loss corresponding to that level J should be within a limit for a reference model. So if the reference model is WJ hat, then I want to put some extra margin epsilon so that the loss does not go beyond that norm, beyond that loss, whichever reference model is given. So these are the two main objectives. So in our presentation, we are not showing all the details. In the project proposal, we have laid out all the details extensively. So to end the presentation, I just want to show the algorithm. So can you zoom in? Okay, fine. So we have come up with this algorithm. So the algorithm is fully ready. So the first part of the algorithm is basically doing the privilege loss, which is line number 13, and the non-privilege loss is line number 20. And we are applying the mirror ascent step in line 25, and then the mirror descent step in line 28. So the main contribution is that this DPO loss, it's not so standard. For example, this line 12, because DPO is for generation tasks. We want to use DPO for classification setting. And this non-privileged part, this is standard multi-level classification loss, line 18 and 19. And there we don't want to use DPO. Here we want to just be agnostic corresponding to some reference model.
So is your goal only classification here?
No. So the classification is one part. Later we'll also do generation. And in term, and the Simpio paper that he has presented, the Simpio loss can be incorporated in line 12. So we also have the plan to incorporate Simpio and CPO. CPO is another reference optimization method. So yeah, this now we'll do some experiment and see whether it works.
Discuss this further during the project.
Yeah.
It's a good motivation.
Yeah, thank you.
Any questions? Next. Anyone?